Okay. So, okay. All right, everyone, and welcome back. If you are new, hit that bell icon button and do that. So, from yesterday, we have started learning LinkedIn, and we have covered some prerequisites before moving to linked list. We was creating our own linked list in Java. So let's move forward and see what we can do next and what we should work on now. Okay. So let's come here, and this was the tab where we was learning linked list. So move forward. Okay. So what we are going to do here, yesterday we have covered this, but let's say it again, and then we will continue. Okay. So let's remove this for now. And what we have covered in yesterday's lecture, if we want to recap that, so the simple thing was this, that we have okay, wait, we have a class. Okay, we will create a class, and we will create a class, and the class is a blueprint for objects. Okay, so now for linked list we need to create nodes. Okay, so we can assume that we have a class for node. This is the class for node. Okay, this is a node class. Okay, now in linked list, inside each node we will have we will have okay we will have data, the type of data we want inside that linked list, and second we will have data, and second we'll have a next is node. Okay, it's a object of this class. Okay, this nodes class object, because the next will store reference to another object, so that's why the next will be nodes class. Okay, so this will be object of this node class. Okay, so this is what we have learned yesterday, and now let's move forward. How we have learned that in yesterday's lecture, how we can create classes, and how to use them, and everything that we should know before moving toward linked list. This wasn't advanced link oops concept, but we have covered basics. So now what we are going to do, your answer, okay, so I have passed this yesterday. What I would like to do is memory become this. Okay, no, we can't access 10 exactly. Okay, third. Now, here is the big idea. This is why we almost never do this. This is why we almost never do this. Okay, head is equal to head dot next unless we are intentionally deleting the first node. Okay, so what happens in linked list? So let's cut this. Inside node links, we have multiple nodes. So let's assume that for now, okay, these are our nodes. Okay, these are the four nodes we have in our. Okay, let's cut this. Wait for a while. Okay. Hello, bro. Any question? So in linked list we have nodes. Okay. So let's assume for now we have four nodes in linked list, and how these are connected. All these nodes are connected like this, and it will be connected like this. Okay. And what connects them next? Inside each node we have next, which connects our node. Okay, so let's come here, and inside this we'll have a next, which stores reference of this object. Okay, so now The next is store reference of this object. We will store this is connected to this node. Okay, so okay, let's get this. And its next is store reference of this node, so that's why this is connected to this. And it is store its next stores reference to this node, so that's why it's connected to this. And its next stores null, as you don't have any other nodes forward, so it will be something like this. And our first node, if we want to ever access it, it is head. Okay, we call this head in linked list. Okay, this is head. Okay, this is the head. And our last node here before null is called tail in linked list. And we haven't covered this till now, but we'll understand this later. So the first node is head, because we will need to access our first node many times, like we want to perform action that we want to add any node before this. Okay, before this node. So what we will do, we will have a head, we will use this to insert any node before this node. Okay, so what happens, so let's write it. We store this first node in head. And after this null will have null. Okay, as we don't have another node further. And this is our tail node. Okay, our last node is called as tail. The main thing we will talk about is head, because this is what we will be using mainly throughout the linked list. If we want to access any element, we will use this. And everything, for many of the use cases, we will be using head. So let's understand what the head do. Head stores reference of this node. Head stores reference of this node. So whenever I want to access this, we can use head to access this node, because we don't have any node that stores this node's reference. Okay, so what we can do now, if I ever want to access this node, let's assume I want to access this node, what we can do, we can directly go from this node to this node, because we have head. And with the help of head, we can directly go to this node. And whenever we want to access, what we'll be mainly doing, if you have worked with the arrays, you will understand that whenever we want to access any element from our array, what we do, we pass index. So this is how we will be passing index same in our method, which will be created inside our class later. But what we'll be doing, we will create a get. Okay, let's name it get for now. We will have a get method, inside which user will pass index of the link node he want to access. So he will pass here, let's assume he will pass 2 here. Okay, for this node. So how we will return this node, what we are going to do, from head we will go to this node. The loop will run something like, we will create a new node named temporary, and this temporary will store head. Okay, this temporary will store head, because the temporary will get updated every time we are moving from this point to this point, this point to this point. So we will need another another node to track each node. Okay, we can't move head from this point. If we move head from this point, we can never get our previous element. Okay, so we don't want to lose our first element. So that's why what we are going to do, we'll create a node temporary, and the temporary will store its head's reference, and then we'll go from this reference until we don't reach this point. So our loop will be something like, in while we will write temporary, and until it is not equal to null, let's do some work. And after doing this work on one node, we will update our temporary to another node. So what we will do, temporary will become the another next node. Okay, this is null. This is to traverse complete array. But if you want to reach any point, for example, we have passed inside get any index, this is index. Okay, so what we'll do, until we don't reach this idx minus 1, we will keep updating our temporary, and when we will reach this point, then we will stop. This is how it will work. So let let's get this for now, and get into our code and everything. So let's get here. And what we was learning here is a big idea. This is why we almost never do this. Okay, we will never write this unless we are intentionally deleting the first node. If we want to delete intentionally our first node, then we can do this. But if we doesn't want to lose access of our first node, then we will never do this. Okay, changing our heads reference will result in deleting our first node. Not deleting, but we will never be able to access that node. Okay, instead, when traversing, we create another variable. So whenever we want to traverse in complete linked list, what we will do, we'll create a temporary node here, and the temporary will store head. Okay, I have already talked about that here. And then what we will do here, this is head, then our temporary will move from one node to another node, then another node, until we don't reach the point we want to reach. Okay, so if we want to traverse complete array, we'll go until we don't reach the our last element in our linked list, last node. Okay, so let's move forward. And notice what happened, temporary moved and head never moved. Okay, so we can always start traversing from again from the beginning. Golden rule, head is the only permanent reference to the linked list. Okay, head is the only permanent reference to the linked list. Never move it unless you intentionally want to change the list. Okay, next, module 2, the heap pointer. What is, okay, sorry, the head pointer. What is head? Head is a reference to the first node in a linked list. Okay, so without head, there is no way to access the list. Okay, so using with the help of head, we can access our complete list because we know what is the first node, and then using our temporary node, we can move further to another node, because inside each node we have next to get to our next node. Okay, so why is head important? Head acts as the entry point to the entire linked list. Since each node points to the next node, starting from head allows us to visit every node. Okay. Next, traversing without losing the list. Never traverse like this. Okay, if you traverse like this, you will lose your first node or your previous node. So because you will lose access to the previous node, instead what we do, we create a temporary node temporary, and then the temporary store the reference that we have in our head, and then we keep moving this temporary until it doesn't become null. And what null means, we are in on last node in our linked list. Okay, move temporary not head. Mini challenge: before you write any code, I want you to think like a software engineer. Suppose I ask you to create a linked list class. What variable should the class contain? For example, it have should it store head, tail, size, something else? Don't think about methods. Okay, just think what information should a linked list object permanently keep track of. Okay, so I think these will be head, because we want to store a reference of our first node, so that we can traverse our linked list anytime we want. And next we'll have tail. What is tail? Tail is last node in our linked list. For example, this is, okay, so we have a linked list something like this. Let's change its color to this, and then we have another node. Okay, and same another node and another node. So if we want to traverse this complete node, for that we need head, because if we have a starting point we can traverse complete node. Okay, and second we will need a tail also. It's not that much mandatory, but just to know that if we ever want to add any element in and in at and index any element, then we will use tail for that. Okay, so things that we need, this will be our tail node and this will be our head node. Okay, the first node will be head node and the last node will be tail node. And anytime I want to add a node here, another node here, what we will do, then we will use this tail. Okay, because what we want to do in that case, inside this tail node we will store it inside its next. Before we had null here, but after adding another node here using our method, what we will want to store this node's reference in this next. So that's why we need tail. Using tail will store, tail will be a node. Okay, tail will be a node objects class, no, node class object, and the tail will store this reference. Okay, its reference, this node's reference. So when we will create this node, we will store its reference. And very first, when we create our linked list, what we have, we only have one node in our linked list. Okay, so what we will do in that case, the same node will be head and the same node will also be tail. Okay, so both points toward the same node, but as we add another nodes, we will change our tail and heads value based on where the element gets add, no, where the node gets add. Okay, it depends on, for example, if I add another node here, then we will update our head, and if we add our another node at the last index, then we will update our tail. Okay, so it gets changed as we update our list. And let's get here now and let's explain why we need all these things and also why we need size. Let's understand size. This will be a static variable and it will store size of our linked list. And how we will update it, whenever we perform add operation, we will update it by size plus plus. Whenever we update our size, for example, I remove any element from our linked list, then what we want this size to get minus minus. Okay, so this is how we are going to update our size. Size is nothing but just size of our linked list. Okay, how much nodes we have in our linked list. And this is simple. So something else, don't think about methods yet, just think what information should a linked list object permanently keep after or keep track of. Okay, then it's like you are building JavaScript on list head, so that which will help us to traverse the complete linked list. Tail is going to help us whenever we are adding any element in the last, you know, not element, it will be node. So to access our first node, which will help us to traverse the complete linked list and is going to help us whenever we are adding any node in last. Okay, in the last. Okay, next what we want, that we should also have size, so that we should so have size, that so that the user knows the size of the linked list. Okay, So okay. To access our first node, which will help us to traverse empty linked list, and tail is going to help us whenever we're adding any class. Imagine we don't have tail to add 40. We must start from head. I don't know, brother, who told you to do DSA with Java. It's just extra headache with Java if you. No, by the way, what I think is we have to do DSA and in Java and no, in JavaScript, it is not a good practice to do DSA because there is not that much community around it, or we can say also if we target big companies like MNC companies, then we have to go with Java or C++ or Rust maybe. So that's why we must start from head and then attach 40. A time completion. Now imagine we have tail. Adding 40 becomes time complexity because one variable. So as from traversing the entire list size, again correct. Without it, suppose some nodes are there, we will count every single time complexity this, and with this every operation becomes get size this. So our linked list class becomes, yeah, inside our linked list class we will have all these. Okay, something like, notice something, the class doesn't store data, it stores information about the linked list. Okay, so another think of a train, each coach is a node. Okay, now ask yourself, does the train manager sit inside every coach? No, the train manager simply keeps record. So first goes, that's exactly what a linked list class does. Head manages the node. The biggest mindset shift, many beginners think a linked list contains all the nodes, not exactly. A linked list object only contains head. Tells us the node lives separately in memory. Okay. Example, head is this, tail is this, and size is equal to linked list object. The nodes are not inside the linked list object. The linked list object just knows where they are. Okay. The distinction becomes very important when debugging. What it says, the node lives separately in memory. You are completely wrong. Who told you that there are many good courses and resources in DSA with JS, even Udemy courses and big good problems are in not language. Okay, I know there are courses available, but I think there is not that much community support or people. Yeah, people are learning now DSA in Java, JS, but at that time I don't heard much about it that do DSA in JS. And also I think doing DSA in Java is a better option as it's a oops okay, as we have Let me search. I researched about it at that time, but for now, what I should say, I would like to search here what is better to do, DSA in Java or JS. Let's get into Java is generally better for learning and interview for data structure because it features strict typing, better instant data section framework versus XML by tech companies are superior choice if you are aiming for front-end roles or already have extensive experience with the language. Okay, so that's why I choose at that time Java. My goal wasn't that to, but I think it's not that much complex. Learning any language is not hard if you already know any programming language. It's just a little syntax changes and okay. And yeah, as you can see, we don't have built-in DSA libraries mainly in JavaScript. So these are the some reason I moved to Java for DSA. So let's get here and notes. Write these down. Linked list class. The linked list class is responsible to manage the entire state, and we'll have this. Okay. It keeps track of head reference to the first node, reference to the last node, number of nodes in the list. So this will be something like responsibility head is starting point of the linked list use. Okay, the list cannot be accessed. Tail points to the last node makes insertion at the end is efficient. And size store the total number of nodes and returns the size instead of traversing the list. And first coding challenge, now we are okay. We are finally going to write our own linked list. Okay, linked list. I don't want to copy my code. I want you to write it. Create these two classes. We will create two classes, node linked list, and requirement implement only this much. Okay, class node. Okay, and data node constructor and class linked list. We will have node head, node tail. Okay, what we are going to do, we are going to create two class, linked list and node. Inside node, what we will have in data node next and a constructor, and inside linked list we will have a node head and node tail and int size. Okay, so don't add any method set at first. We will not add this, but let's get here. And as it says that we should have two class, what I will like to do is create a new file, practice, or I would like to name it linked list dot java. This is our linked list class, and next I want to have, can you create something like two class inside a file? Yeah, so let's create it. Inside node we should have int data, and next what we want is node next. Okay, which will be null for now. Default it will be null, but if I create this in this way it is okay. Next what we are going to do, we will create a constructor here, and inside this constructor what we are going to do, we will take data from user in this constructor. So let's get data in this constructor, and let's set this dot data to data, and next dot, okay, this dot next will be equal to null, and this is what we want. And yeah, yeah, next what it says that we should have a linked list class inside which we will use this node class for head and tail, and we will have a size. So let's get directly into it, and node, and it will be head, and node tail, and int size. These are the three things we will need, okay, inside each linked list. Okay, so let's get here, and don't add any methods, write it yourself. I will review it like a senior developer doing your point out improvements, and okay, let's submit it here. Okay, review node class, perfect constructor, perfect. One interesting thing in Java, this is optional. The items are automatically initialized to null, so this should also work. But should you write it? I prefer writing it while learning because it clearly communicates your intention. A newly created node doesn't point to anything yet. Later, when you are comfortable, you can omit it. So let's get here, and we can write here that it's optional to. Okay, it's optional, or you can directly write optional. Okay, Control Z. Okay, it's actually optional because the object reference. Let's copy this here, and next what we are going to do. And at this point, I don't think you are just going to take now. The real linked list begins. Until now, we have only built the structure now. So our first method we are going to implement at first. Before writing any code, let's think like engineers. Suppose the list is empty, and now we execute this. So after this operation, what should head point to, and what should tail point to, what should sides become, and question most important, should head and tail point to different nodes or the same node? Think carefully, and this is very first. Okay, so I have already told that here that at very first, when we will be adding our first element, we will be pointing toward directly our. Okay, our head and tail will point toward the same element. Okay, so tail will point toward this, and head will also point toward this. And as we add another nodes, our tail will move or our head will move based on where we are adding that element. If we add at first point, at first index, then we'll move our head, then we'll update our head. And if we add another nodes after this node, then we'll update our tail. Okay, it depends on where we are adding our another node. And also that next, we will update our size whenever we are adding at first or last. It doesn't matter. If we are adding at first, we will do this plus plus. If we are adding at last, the size will become plus plus. And if we are removing from first or last, we will keep it minus minus. Okay, so let's get here, let's write it here. So let's answer this all question 1 is equal to, what should head point to? Now in one. Where link to this. We only have one node, so the last node in. Okay. What should size become? 1. 1. Question 4. Should head and tail point to different nodes or same node? Think carefully, and this is very large. Same node. And if I say Anur, for this master class, from this point onward, I'll feel like your DSA interview for observation at last remove. First, we'll follow this process, understanding the problem, draw the memory diagram, think about edge cases, design the algorithm, write the code, run it, and okay, it is cut interview pitfalls and solve a related read code problem. So let's submit it. Let's visualize it. Okay, initially we'll have head is equal to null, tail is equal to null, and size equal to this. Now we call this. The first thing we will do is create a new node. Okay, this is the first thing we are going to do in our first. Okay, at first let's understand how this works. So some of the methods we are going to write in this linked list is first, at first, second, at last, and then we will have admit. Okay, admit, but we will name this method add, and this is not admit. This is simply that wherever we want to add in our array, in our linked list, what we will be doing, user will pass here the index at in which index you want to add this node, and then we will pass a data here. Okay, so these are the two things what we will take from user, and then we will add this data at this index. Okay, so this is what we are going to do in this, but for now let's focus on the add first, how this works and how we are going to write the logic of this. Okay, so first we will create a node because we are going to add a node here, so we need to create a node. So what I will do, inside the node linked list class, I will create a node, and the node will be something like node, and we will name it new node equal to new node, and we will pass the data inside it. Okay, the data user will pass us, we will pass the data inside it, and we will do all this work inside our add first. Okay, after writing this, what we are going to do, okay, after writing this, we have created a node. What we want to do now, we will, if our head is equal to null, if our head is equal to null, what it means, if head is equal to null, we don't have any elements inside our linked list for now, then what we are going to do, the head and tail will now point toward the same node. So head will be equal to tail, and the tail will be equal to our next node. Okay, so now both points toward the same node. Okay, this is the first thing we are going to do, and next what we are going to do here, this is our as case. that if we don't have any node in our linked list, we will make the head and tail. Okay, we will point our head and tail to this node. Okay, so this is the statement which will manage where our head and tail should point. So the head and tail will point toward this next node if our head is equal to null, because head is the main point. Okay, next what we are going to do is, after creating this node and doing this, we will anything that is needed. Next will be null for now, so it is by default. Do we need to create it? Let's see. Okay, after creating this new node, what we will do, memory, inside memory we will have a strict new node, and in heap we will have this. At this point our linked list still look like this. Our linked list still look like this. Okay, we will also update our size here. So here we are going to update our size plus plus. Okay, next come here, and now memory becomes linked list and head and tail, and this is size 1. Now we connect it. Okay, so what we have done, the node exists but it is not part of linked list yet. Now we connect it. Since the list is empty, what we are going to do, head will be equal to next new node, tail will be equal to new node. Now the size will become 1, memory becomes this, head and tail both points toward the same node, and size will be equal to 1. Okay, so this is the linked list object. And okay, notice something beautiful, both head and tail points to the same object. Why? Because there is only one node, and that one is okay. So let's get here. This is called an else case. Whenever you implement a linked list operation, always ask yourself, what if the list is empty? What if it has only one node? And what if it has many nodes? Okay, these three cases appears again and again. And now come to the interview part. Imagine I ask you implement at first. Modification implemently start writing code. I don't. I ask first as, what if the list is not empty? Suppose contains head. We already have this is our tail, and we want to is okay. Let's understand this now. From this example we can understand better how our code should be. For at first, we have a linked list something like this, in which we have 10, 20, 30, and we have null. Okay. Okay, so this is our node. 10 points toward 20, 20 points toward this, and 30 points toward this, and 30 is tail here, and 20 is head. Now when we will add first any element at first index, so what we are going to do, the add first, let's assume that I call this add first with 5. So first our if condition will okay, first we are going to create node. Okay, let's write our steps in white. So first create node. First we will create node. Second, we will check our age as case that if this is equal to, if our head is equal to null, then what we are going to do, we have already talked about that. Third, what will be the third case? Okay, what we are going to do here is that if we already have nodes in our linked list and we are adding this at first, then what we will do, I will like to inside this new node, it will be new node. Okay, new dot next will be equal to new nodes next will be equal to heads next. Okay, heads next. Okay, because what it means, if the else case doesn't run, if it runs, okay, if it runs, it means we only had one, we don't have any nodes in our linked list. But if the else case doesn't run, it means that we have some nodes in our linked list. So what we are going to do, if we have some nodes in our linked list, so what we want to do is that the new node will store its reference. Okay, okay, it will not be head dot next, it will directly head for now. And now the fourth step will be the head will be equal to this new node. Now the head points toward the new node we have added. What is happening, what we'll do first, our new node we have created, the new node we have created. Okay, first what we are going to do, when we create this, we will store the data inside it. What is data? Data is 5, we will store this. Okay, then we will check as keys that we have any nodes in this linked list or node, not. If we have we don't have any node inside this linked list, what we are going to do is we will add this directly in our linked list, and this will be tail and head. Okay, this will be equal to tail and head. Okay, so it's easy to do. But then if we don't if the linked list is not empty, then what we are going to do in that case, let's say let's write it here. We have created the node, and still the next is empty. Okay, for this the next is empty, and this is not head, still this is not head. Okay, so how we will add this node here before 10, how we will add this node here? So what we are going to do, first what we want, the next should store this address. Okay, what we do always, our node stores its next node's reference. Okay, so what we want, the next should store this reference, as we are adding this at the first index. Okay, so what we are going to do, our head stores this object. Okay, our head stores this node, so the head have its address. So what we are going to do, the new node's next will store its next will store head. Okay, so that's why we have wrote this statement that new node dot next will become equal to head. Okay, the head is reference for our next element. Okay, before. Okay, next what we are going to do now, as we have pointed its next to this element, we will change our head to this. Okay, now what we will do, we will update the head equal to new node, because what we want now, when we will add a new element here, now we will have another element 5 here, and this 5 points toward this 10 using this next. Now we want to move this head from here. Okay, not like this, we want to move this head from here to here. Now the head will point to this. Okay, this is how our get first, no, add first works. So let me write code for this. I will like to write this I will name this void int, and it will be add first. Later we will understand it. No, it's not void, it will be public int. Okay, and what I want, the add first will take data from user, it will take data from user, and what we are going to do inside this is we will have can we write this directly here? Let's write it directly outside for now, and let's see, can we access all these variables or not, because we have to access all these variables, or let's see. So what we will do here, first we will create new node. Okay, so the node will be new node will be equal to new node, and we'll pass the data here we are getting from this add first. When we will when we will call this method, we will pass any int data, and then we will create a new node related to that data. Then our edge case, okay, this is our edge case, that if head equal to null, the head is inside linked list. How I can use this head? mm, new node dot no. For now, I don't know how to access this from here. So what I will do, I will directly, let's assume for now we have something like private static, no, public static head. Okay, this will be equal to node. Let's create this for now, and public static node tail. We can access them later. Okay, accessing from this is not the main problem. We just have to understand, then later we will see how to access these node and head, tail and size. Okay, so what we'll do here, first I will like to update our size. So we are also going to have size here, public static int size, and I will like to update this size plus plus, and if head is equal to null, what it means that we don't have any node in our linked list. Then what I will do, I will make head equal to tail, and the tail will be equal to new node. Okay, so it means that new node will be head and tail both. Okay, now next what we will do here, that if we have some nodes in our linked list, what we are going to do, that is the new nodes next will store head. Okay, now the new nodes next stores our next nodes reference. Now we are going to make this new node head. Okay, so the head will be this new node. Okay, this is how our add first works, and the same our add last will be here, but we have to make some changes there, a little tweaks there, and so let's keep this for now, and let's come here and see how it works further. So let's get it. Before we write any code, I want you to think only in terms of pointer changes. Question: after inserting 5, what should the final linked list look like? Draw it, then answer these two questions. What should 5 dot next point to, and should tail changes or stay the same? Okay, so first I would like to draw. Okay, so let's draw how it will be. It will be head, 5, and then we will have 10, and then 20, then 30, and this will point toward null. Now what we are going to have, we will have, and this will be equal to tail, and now answer the first question, that what should 5 dot next point to, 10, and next should tail changes or stays the same. So it will be stays, okay, stay the same, because we only in start. Okay, final linked list before. Okay, and after this question 1, what should 5 this correct, and should point to the old head node. At this moment the old head happens, Okay, to content 10, the distinction becomes important later because we don't know what data the head contains. We only know it is the first node. Okay. So next question 2, should tail changes? Your answer stays the same. Why? Because we inserted at the beginning. If we had inserted in at the end, then we have to change this. Okay. The last node never changed. So now comes the most important part of add first. We are not going to write the code immediately. Instead, we are going to design the algorithm. Imagine this initial list. Okay, is now we create new node. Okay, this memory will is create a new node. This okay, new node head this. Currently, the two lists are separate. My question, you now have two separate pieces, 5 null and this. You want to combine them into this without writing Java code. Tell me the exact order of pointer changes. For example, step 1 is step 2, and think carefully. This is one of the most important interview question. And there are only two pointer assignments, ignoring size plus plus. One wrong order can destroy the entire linked list. Okay, so what it says that you now have two separate pieces. When we do this, node, new node, and new node is equal to 5. Now inside our memory we have a new node, and we have this. Okay, so what we are going to do is we want to combine them into this without writing Java code. Tell me the exact order of pointer changes. For example, this, think carefully. There are only two pointer assignments. One wrong order can destroy the entire linked list. I want you to figure out to must happen first, and this is step 1. After creating node, I will like to element. We have nodes in this linked list. Data sending node. Okay, and if it is equal to true, then what we are going to do, head equal to tail equal to new node. And step 2, if we have multiple nodes as case will not execute. So yes, new nodes, new nodes. Next, and the head is hello bro, any question? So I will Okay. Step 1, create the node. Correct. Step 1, handle. So root. And don't forget, yeah, we'll also have this. And we'll discuss the return in a moment. Okay, yeah, I forget that. Okay, so what we are going to do after managing this, we are going to return from here. Okay, return. And okay, let's cut this. And if head is equal to this and doing this, will the method must return a result of type int. No, it will be void. And this is correct order. Now let me show you why the order matters. Suppose someone writes head is equal to new node and looks similar, right? Let's try it. What is going to happen if you do this? Now the head's value changes to our new node which we created. Now if we change new node dot next, it will store its self's reference. Okay, it is not storing the next node's reference, it is storing itself's reference. So that's why we have to do it this before and this later. Okay, so initially this you can also see that what is actually happening inside memory. So memory becomes this. Okay, so what just happened, you lost the only reference to the old list. Where is 10 now? Nobody knows, the entire list is gone. Now execute this. And but what is head now? Okay, it is new node, so you get this. Okay, or this, the node points to itself. You accidentally created a cycle. Okay, this is a classic linked list bug. Okay, that's why we always remember golden rule 4, that never override a reference before you have saved the path you still need. Okay? And so this is the correct order to do it. One tiny improvement, you wrote head is equal to null. Excellent. Now think like an interviewer. After doing this, so the method continue executing the remaining code. No, we have to return. Okay. So should that happen? No. Why? Because now head is equal to this, and if we execute this, then the head is already new node. You will create this a self loop. That's why we immediately return. Okay, so we have to return immediately from here. Okay, final challenge. Before coding, I think you have earned it. Okay. I don't want to write at first for you. You write it requirements, create the new node, handle the empty list, and then the normal case update size. Use the correct pointer or when explaining why each step is done. Writing code that another will read in 6 months. What I will do, we will have a void new. Okay, add first this here. Okay, so let's copy this, paste it here, and now I can cut this. Okay, this is how we can write our method inside linked list. Okay, so let's cut this. Now we have created a node. Okay, and this will be used to create each node, and these are the linked list thing that we want to have in our linked list. Okay, so this is what we are doing. Okay, so what we are going to do now is yeah, we have done this, and I would like to write comments, create node. I will like to update it here directly. Update size. Now the next will be third. What we are going to do is manage as cache, I'm updating this here because it now it doesn't matter we do this operation or this. Okay, we will update state here. Now next, what we will do, create node, and if we already have nodes, nodes ref in. So create node at first index. If we already have node and nodes in linked list, and store next nodes ref runs in new. Okay, let's keep it. Okay, so let's copy this and see that is there any problem, or we can. Okay, we didn't manage some things like handle the empty list. Okay, we have done this. Okay, no problem. So code review, I'm going to create one, update size, manage as case, and then create nodes surface. Your education center, take okay. You would pass this all this test, but what I like most, you wrote comment. Ignore stone, go to player, explain why not just word. You handle the as case first accident that makes the first of the pointer order is correct. This is the biggest thing you remembered. Instead of this, what would be ring? Okay, which would be wrong? Minor improvements that they are not correctness issue. They are about writing linear code. So what you can do, instead of manage as cases, write handle empty list. So I would like to change this handle, and this improvement create nodes first. We already have nodes. I will replace this with point the new node. Okay, and now what I want, improvement 3, that is the instead of size near the top, many developers prefer. We can also do this, okay, because this size changes only after insertion succeed if there is any error. So that's why we can manage this in this way. Is your version wrong? No, it is perfectly valid. It just depend on coding style. So I will like to change it. Okay, so size plus plus, and now let's cut this and this. Okay, interview rating, implement at first from memory. I will rate it. Okay, overall non-point, the missing GUI only because of comment wording, not because of logic. But now I'm going to challenge you. Don't add first motion think. Okay, now let's. I don't ask question. Okay, suppose you remove tail from our linked list class. Okay, can you still implement at last? If your answer is no, why not? Until if the time complexity we don't write code, think like an engineer. This question tail exists, and instead of just accepting that it does. Okay, let's get here. And let's see what will actually happen inside memory. Okay, so what we are doing, let's add this here. What it says that suppose we remove tail from our linked list class. Okay, let's assume that we have something like this is Okay, let's create a linked list now. So I will like to create multiple small boxes, and then let's copy them, paste it here, and then I will like to, okay, let's keep this. Okay, so let's change color to this, and these are our linked list nodes. Okay, so let's let's come here. Okay, so these are our nodes in linked list. So what I'm going to do, well, let's create a pointer from here, and next I would like to create another arrow from here to this point. Let's keep this to this. Now let's write text. First let's change this. Keep it small. Keep it small. This is head. This is tail. Now if we perform at last, we will pass data here like 40. This is 5. This is 10. This 20. And this 30, 40. Now we are adding 40. Okay, we are calling add last, and what we want to add this 40 here. Okay, yeah, we have null here, but when we will call this function, we will add this node here. So what is going to happen, let's see that. If we have tail, what we are going to do, the process is simple. Tail is equal to last node, we know. Okay, what is tail? Tail is our last node. If we only have one node in our linked list, then the same node will be tail and the same node will be head. But if we have multiple nodes, then the last one will be tail. Okay, I have told that lots of time, so it will be clear now. So what we are going to do here is, if we have tool, then the logic will be this. Our atlas logic will be this. We have add last, and we'll call this with 40. Okay, this is our add last method. Now inside this, what we want to do, our first task will be to create node. Okay, so I will create a node here, like node, new node, equal to new node, and we will pass the data here, which we get from this add last. Okay, so this is how we will create node. Second, we also have to handle our as case here. Okay, so what is the as case? As case will be same what we had in our at first. Okay, so the as case will be same, nothing will be changed, same as that was. Okay, so same if condition to manage as case. Okay, so what we are going to do, it will be now if head equal to null, then we are going to make head equal to tail and tail equal to new node. Now I would like to move this statement a little here. Okay. So here we will create our new node, and here we are managing our edge keys. Okay, we have done these two things. Now what we want to do next, if we have tail, this is the condition for tail. Okay, if we have tail, then this will be our logic. Now then our tail will be something like this. Okay, this is simple case. And if we have one node in our linked list, then we will also have tail, then the condition will give us false. But if we don't have a single node in our linked list, then this will give true, and we are going to perform this action. After performing this, we are going to update our size, and we will return from that condition. Okay. Okay, this is what we have to do in this edge case. Now our third condition will be is that what we have to do, uh, this tail this tail stores last node. Okay, last node. Okay, but the last node's next is equal to null, because we don't have any node after this. So what it is to stores, it stores null in its next. So what we want is that when we add this node at last, this should store its reference now. So what we are going to do is, now the tail dot next, as the tail is equal to this node for now. Okay, we will update the tail dot next equal to our new node. What is new node? This is the new node which we have created here. Now this stores reference to this new node. Okay, now as it stores the reference of our this node, what we will do here, let's make it a little small, and I will like to, okay, let me get here and let's make this small. Yes. Okay, now I will add another node because the 30 is connected to this new node now. Okay, because we have added its reference in 30 is next. Okay, so what will happen, we will have another node inside which we have 40. So let's add it here, but still the tail is pointing toward this 30. Okay, we have added the node. After doing this, that tails next should store this node. Okay, so now its next points toward this 40. But what about tail? We want to change this tail too, so that later when we add another node at last, we will use this node tail again for that. Okay, so what we are going to do now, the fourth step is that we change the tail dot, now not tail, sorry, not tail, we are going to, no, it will be tail, sorry, tail equal to new node. Now the new node will be equal to this tool, this tail. Now that this will be removed, and our tail will be this element now. Okay, so what is the time complexity here? We haven't run any loop, and these are the constant operation we will be performing through every every time we will be performing these actions every time, so the time complexity here will be big of 1. Okay, we'll perform the same operation. Okay, these are not increasing gradually, so it will be big of n, no, big of 1. Okay, it's as its constant operation. So its time complexity will become, its time complexity will be big of 1. Okay, and also space complexity will be same. Okay, big of 1. So let's move forward. If we don't have tail, let's cut this, and I will like to remove this in a way like cut. Let's zoom it a little, and let's create this, and it will be of this color. Let's create it here. And now what I want, no, control Z, I want to open this, and this will be tail. Okay, no, sorry, now we don't have tail. We are running this for this condition. If we don't have tail, what we are going to do is we can still implement, we can still add our last element, but how? Let's see. We don't have tail, so we don't know what is the last element. So what we'll do here, so it will be something like, when you get in this at last, no, we don't have head, so I would like to remove this from here. And now let's write, this is at last, and inside it we are passing 40. Okay, what will happen? Node, new node equal to new node, and this will be data we will be passing from this at last. Okay, this is the data. So our logic will be something like, first we will create node, second we will manage our as case. So the as case will be as case. So the as case will be, if head equal to null. So what we are going to do, that head equal to this new node, size plus plus size plus plus return, and then this is the logic. Now we are not going to write tail here, because in this linked list we don't have tail. Okay, so this is the complete logic of this, and it's not complete till now, but for our as case this is the complete logic for as case. Okay, now what we are going to do is, after managing our as case, what I want, I will make this small. So okay, this is okay. Now next what I want to do is, after managing as and this, what we are going to do, we will have int, and I am going to create a temporary which will store this head, and what we will do, Then okay, this will not be int temp, it will be node. Okay, as a temporary is storing this will be node temporary, because at the temporary is storing reference of our this element. Now we will write a logic like while. Inside while we will write that until temporary not equal to null, what we are going to do, okay, so the logic will be something like until this temporary node don't become null, what we will do, we will update our temporary is equal to temporary dot next. Okay, and this is the condition where we have to manage our last element adding. So what we will do here, this is completing, and what I will do, temporary is equal to temporary will be temporary dot next, and now this will keep updating. But what I want, when we reach the state where next is equal to null, okay, so what we'll do, if temporary dot next, if temporary dot next equal to null, okay, then we will get into this loop. We are not updating temporary here, we will update the temporary here, temporary equal to temporary dot next. This is the updating condition, and this is our if condition. Inside this if, what we will do, we are going to write the logic of inserting our last element. Okay, so what we will do here, if temporary dot next equal to null, so it means that we are on last node, because the last node's next will be equal to null. So what I will do, I will add inside this temporary dot next. Now the temporary dot next will be equal to this new node, and now we update size plus plus. Okay, now the temporary dot next will store new node, and we will return from here. Okay, now we will return from here, because when the temporary dot next becomes null, we are performing this X operation. So what will happen now, now the temporary will become, now here the temporary will update, and it will become this node which we have it right now. And when we get here, we have a newly added node here, so still the temporary not equal to node, and we will keep running this loop again and again and again. So what I will do, I will return this from here. Okay, I will return from this loop here. So we are going to return from this loop at this point, return, yeah. So this loop will stop here. Okay, so this is what from this function we will return from this point, so we will stop at this loop. So what is happening here, here the time complexity will become, ts will become big O of n, and space complexity become big O of 1. Okay, so what is happening, if we should if we see, let's What is actually happening? Let's see. This loop runs from this loop runs from always the time complexity is worst case and the big O of n is worst case. Okay, this is worst case time complexity. Okay, but if you don't have any node in our linked list, then the time complexity will become big O of 1, but that's the best case. That, for example, if we don't have any node in our linked list, this is the best time complexity. Then we will run this as case, and then the time complexity of this function is big O of 1. But if we have multiple nodes inside this, then this while loop will run until we don't reach the last node, because then we will add this. Okay, so the worst time complexity will be big O of n, and this is what we mainly focus on. So yeah, for this our time complexity becomes big O of 1. This is the problem. That's why we should store our last node in tail. Okay, as it's help us to reduce time complexity whenever we will add last any node in the last. Okay, so can we still implement add last? Yeah, we can. How? We'll write that. If your answer is no, why not? And then tell me what would the time complexity be. Don't write code, think like an engineer. So let me write it here. So I will if your answer is yes, can you still implement? Yes, we can. How? We will create new node. Second will be manage as case in case we don't have nodes. We this why. Third, that loop, not loop, that loop is loop, no condition. Or I will return from it will be best to write. Third will be create a temporary node which stores reference of head. Write a while loop and keep moving. We don't reach null. Inside it, write if condition which checks that the time dot next equal to null. If yes, we will add time dot next equal to new node. Size plus plus return and no, after we have temp equal to dot next, which will to reach last last node. Function time complexity big O of big of n as well the if we don't have any add in any node in if we don't have any node in linked list, okay, but worst case the time equal to 0. Okay, I can actually see the difference in your thinking compared to the beginning of this session. What code do I write? How do I reach the last? Can you implement LS without tail? Yes, your algorithm great. Handle the empty list. These are the same as case. Create temporary is equal to head perfect. Notice how you are day following. Never move head. Instead traverse until the last mode. You wrote keep moving until you reach that almost. The only thing I would think careful of until null. Where are you? You are already past the last mode. Can you do? It didn't understand what I said, maybe. So I will like to pass. Okay. While this is not equal to. Okay. So this is also correct. Okay. What we are doing, temporary dot next equal to null. Instead we stop one mode earlier, the condition should conceptually be keep moving while the next node like this. In other words, this now the temporary is last node. Yeah. Now you can simply okay, that's the problem. Maybe what we have done. Let me check what we have done here. Next temporary dot next equal to null and this equal to this. What I'm also checking is that inside if I'm also checking that temporary is next equal to null. If this yeah, I have managed that in our if, but let's go with this. Okay. Now you can safely do this. Time complexity you said will correct. You also with tail you also notice with tail the time complexity is bigger for one because it makes insertion at the end constant time. One is small tip where you wrote big of one tiny correction. Okay, it will be big of yeah. Okay, that's so capital big of and not the number zero. Same for this interview notation. What I'm really happy about, okay, one more challenge I want to see just a traversal. Suppose you have this, I write this. When the loop finishes, what is the value of temporary? What happened to head? And can we accept entire linked list starting from head? Yeah, we can use this for size if you want to. No, not size. If you want to create every node in our linked list, then we can use this. But what I will like to do now, I will like to explain my logic to this. So I know that the code we have written before, is that correct or not? Okay, so I would like to write before moving forward, I would like to know that the correct or not. So I was that thing in. So let's write it. While temporary not equal to null, what we are going to do? I will write if condition, if temporary dot next equal to null. What I will do, I will update here temporary dot next equal to mm, new node, and after doing this, what I will do, I will update this size plus plus and then return, and we can also break from this loop, but let's do this and see what happens. Okay, so we will directly return from the function. This is what I want to do, but let's see. And here we are doing temporary is equal to temporary dot next. Let's cancel. uh, this is exactly how you should learn DSA. Don't just accept your code is wrong or your code is right. Understand why your loop is this. Okay, so I have written this. Is it correct? Yes. Is it is logically correct? Let's try run it. Okay, so what is happening? Let's try run it. Initially linked list is this. Okay, so the temporary is had, now the temporary is equal to this. Now check temporary dot next is equal to null. Not no, so we will move this. Okay, now the temporary becomes 20, and now the second iteration again, this is not equal to null, we will move this. Now the third iteration, what we are doing, the check if this temporary dot next is equal to null, is it true? True. So what we are going to do, we will execute this and return from the function result. This is the result. Okay, done, perfectly correct. Then why did I suggest this? Because it is simpler. Let's compare. Yeah, this is simple, we don't have to add if condition and then return from that. We can do this, but yeah, the logic we have written was, the code we have written was correct, and we can also go with that if you want. Okay, so let's, inside the loop you have while loop, if condition, return pointer movement. Simpler version will be this: no nested if, no return. The loop itself guarantees when I exist, temporary is last node. Okay, now so after the loop you simply attach the new mode. Which one is better? Let's compare. Your version correct works slightly more code, nested if. Standard interview version. Okay, ठीक है. Here is something important. Many beginners think there's only one correct solution. That's not true. Okay, yeah, we know that. Both are correct. This is what senior developer do. A senior developer doesn't ask does it work. They ask is readable, simple, can I developer understand quickly. There is unnecessary branching. I'm actually like, do you know why? Because you didn't memorize any question, but drive it yourself. Your brain thought I will keep the list, and when I find the list is equal to none, I will teach a new node. Okay, yeah, I can't teach someone to drive an algorithm if they only memorize it. Okay, so what's next? Is your root temporary dot next should be new node, not equal to sorry. Okay, this was the error, but here we have written this correctly. So what I would like to do next, let's see. So today you are not learning English, let's continue further. I have entering the fun part. Up until now, we have been building the foundation. From here on, every operation you will learn will feel much easier because we have understood this, why pointers order matters and how traversal works. Model for traversal. This is probably the most reused concept in linked list. If you understand traversal, you can solve around 70% of linked list interview questions. So this is okay. What is your first instinct? Most beginners say if head is not equal to null, and we will print this, and then head is equal to dot next. Yeah, we will use temporary here. Okay, so this is just for explanation purpose. It looks fine, but it does destroy the linked list. Why? Because after the loop finishes, head becomes null and you have lost the entire list. So what we'll do, we'll create a temporary node here, and which will store the reference of our head. And now we will move this temporary from start to end. Okay, and then we'll keep printing. So this is for traversing. Okay, so first iteration this, and now move temporary is equal to temporary dot next, and the second iteration, third iteration, and fourth iteration, temporary becomes null and loop ends. What happened to head? Nothing changed. The linked list is completely safe. Golden rule 3. Okay, rule 5, traverse with a temporary pointer, never with head. Okay, so we already know that. Let's move forward. Let's implement print. Don't write code yet. Okay, I want you to design the algorithm. Question 1, what should happen if the linked list is empty? What should happen? Example, head is equal to null. Should we print linked list is empty? Print nothing, throw an exception. And what would you choose and why? I will like to print null or linked list is empty. These are the two things that we should go with. So what would you choose and why? Question 2, suppose the list is 10, 20, 30. How would you like the output to look? I would like to look this. Okay, option B. Option C, something else. Choose one and explain why. Okay, question 1. But before writing all this logic, what we are going to do, I will like to write or add last logic in our code, as we haven't done that. Okay, the thing we have done was just we have understood how the at last works with tail and without tail. Okay, and versus time complexity. So the best way is to now write the method here. So I would like to write void at last, and we'll take data from user, and first we will create node. So let's create node. New node is equal to new node, and now what I will do, as case, the as case will be same, and what we will use here, we are we will use tail here. Okay, not using tail was just for understanding purpose and how it works, but when writing actual logic and implementation, we will use tail. Okay, so if head equal to null, what we will do, head equal to tail, head equal to tail, tail equal to new node, and size plus plus, and we will return from this. Okay, this is what we have to do. And next, here we'll have okay, I don't, let's not write comments for now, as they will take extra time. So what I will do here is tail dot next, as the tails node for now stores in next null. What we'll do, we will store this new node, and now we will change the tail to point to this new node, as this is the last node now. Okay, so this is what we have to do. I will like to update size here too. So yeah, it is great now. Now let's see how we have to work with print. Okay, next method will be void print. If we want to print our array, okay, no, our array, not our array. If we want to print our linked list, then we need this. Okay, so what we are going to do, not this. So what we are going to do, in print we will take nothing, we will directly go here, and I will like to create node temporary equal to head, and while temporary not equal to null, I will keep moving this temporary, and let's print here. Okay, so what we are going to do, show, and I will like to print the temporary here, temporary dot data. Okay, this is simple. I don't think it's confusing because we have understood that how temporary goes from this to this. Okay, so what I will do next, temporary dot data, then this, and it will be printed in this order. And after printing this, I will like to get a line here, and we also have to update our temporary here. So what we will do, temporary is equal to temporary dot next. Okay, this will keep updating until we don't reach our null state. Okay, and now let's get here, and this is for next line, and it will keep moving until we don't reach this, and we are printing this. Okay, so it's okay. And let's see how the print works. If we want, what we can do is inside this, okay, let's get here public static void, and what I will do, linked list new, no, I will call this linked list, and new linked list, and we don't have to write anything till now. What I will do, dot add first, and I will add 10, 20, then 10, and now I will change this with at last, and this will be 40, no 30, then 40. So what will happen now, that first we will get 10, then we will get 20, then we will get 30, and then we will 40. The linked list will be something like 10 first, then 20, then 30, and then 40. Okay, this will be the our link, this will be the linked list. Okay, so I will like to print it here, ll.print. Now let's get here, clear java c linked list dot java, java linked list dot java. You can see here, this is the linked list. Okay, so if we are on the last, I don't want to print this. Okay, what I want is, if temporary dot next is equal to null, then I will directly print it. Okay, so I will print it without this, or else I will print like this. Or you can directly say, it can be more simpler if you want, using ternary operator or using a create, and using a variable which stores values that what we have to print, but let's skip that for now, and I will be directly print this way. Okay, now let's get here, and if we print this now, we will not get this at the end. So you can see here, we are not getting this here. Okay, so let's clear it, and this is our linked list. If you want to have a little space before and after this arrow, so you can click this, and why I'm creating the arrow sign, because it shows that the 20 stores reference of this variable, and 20 stores reference of this, and 30 stores reference of this. Okay, so that's why. So let's get here, and if we don't have, if head is equal to null, also what we can do, that if this is null, we can directly print null here, we can directly print null. Okay, we can directly print this, but printing null is not possible, so we will write this in this way, and we can directly say null. Or if you want, you can say linked list is empty, and linked list is empty. Okay, sorry, this is not like this. If we are on last, we will like to print null, and if okay, not this. If head is equal to null, if head is equal to null, then if we don't have head, then what I would like to do is Siju. Okay, so what I will like to do is linked list is empty. If we don't have anything inside our linked list, so that means our head will be null. So I will like to print directly here that the linked list is empty. If user is want to print the linked list and we don't have anything, we will print this. And if we have any nodes inside our linked list, we will print that in this way. So let's print temporary.data directly and just keep it as it is for now. Now it works perfectly. If I get here, this is how it will behave. And if we don't have anything inside our node, let's assume that the linked list is completely empty, comment it out, and let's print it now. Okay, now let's see what it prints. Clear and print linked list is empty. Okay, so it's working as expected. So let's get here. Question 2, suppose the linked list is the list is 10, 20, 30. How would you like to output to look? Okay, the output to look. Option A, option B, option C, something else. Choose and explain why. Okay, let's get here. Question 1, what should happen if the linked list is empty? Example, head is equal to null. Should you print? What would you choose and why? I would like to print a linked list is empty. Mm, we don't. No, printing size is not a good. Okay, so I will like to print linked list is empty because that tells the user that we don't have anything in our linked list till now. Second will be, suppose the list option B because looks that 10, 20 to 30 and 20 to 30, 30 to 40. Okay, 30 to nothing. So let's print here null. Okay, so I will like to print null here. Let's get here B because it looked like the 10 is connected to 20 and 20 is connected to 30 and 30 to nothing. Okay, yes, that's exactly competition that this is a program hosting the body from one code and Empty is completely valid. Why imagine someone write this and nothing appears? They might wonder did the method run? Is there a bug and list empty? Protection libraries. This is really what I would choose because so the structure of linked list. If you print this, you only know the values. You don't understand the length. So when you print this, you immediately you okay. One is instead of linked list is empty. I will improve this with linked list is empty or empty linked list. Okay. Now comes your first independent method. I want you to implement require. This is empty. Otherwise, this use stamp while don't modify head. And one hint: think carefully about this line. Should null be printed inside the loop or after the loop? This while temporary is not equal to null, we will print this. If temporary dot next is so yeah, the better approach is this. We can do temporary dot next is not equal to null, and at any point this becomes null. What we will be doing? Okay, so what we will do here? Let's cut this completely, and until this is not equal to null, I will print this. Okay, we will keep updating this, and now what we can do? If temporary dot data is equal to null. Okay, it will not be temporary data, it will be temporary dot next. I can directly do see show in 12 we print and then next. Now we have less lines of code and it works as our previous code works. Okay, same as our previous code works. So let's get here clear and Java C, no, Java linked list dot Java ILL is empty. Mm, thread means order. I cannot read fit next because local one is null. What is the problem? Exception is thread. Okay, we have to return from here. Okay, let's get here. Yeah, the problem is we don't have temporary. Then this will return an error because we are running this if statement and what it says that we don't have temporary dot next. If we don't have head, then we also don't have temporary dot next. The temporary here will be head. So what I will do, let's come here and we will use this here, and now we will run this, and this is for next line. And now let's comment out and comment all these lines, and let's comment only this line. And now let's see, it prints as expected. No, next. This is printing next, but I want to print null, so let's print this here directly. Yeah, this is the better approach to print it. So let's copy this. Challenge try writing is complete. Don't worry if it I have already written at last in the first video. Okay, what is the problem? Let's try run it. If while temporary dot next not equal to null, okay, this is the problem. Maybe what we are doing, we are skipping this element. Okay, yeah. So what you can do for this is if we skip this in this way, this is the problem. Doing this is the problem. Okay, temporary dot next equal to null. So what we should do is not this until temporary not equal to null. We will keep running this and we will print this. And yeah, let's get here. We can see that here. And the problem is we'll skip one element. We never printed 30, so output becomes this. And why this happen? Because of this. The simplest fix is that until this is not equal to null, we will keep running this and print ln null. Okay, we will print ln this in the end. Yeah, this is the great, this is better way to do it. So yeah, let's copy this and paste it here. We will paste this here and let's remove this statement now. So this is better way to write it. This is how we will be printing it now. So let's get here. This teaches an important relation that for at last. Notice how we used for at last, but while print in at last we wanted to stop at the last. And okay, in print when this so it's enough for today. And if you are new, hit that bell icon button and do like. So take care everyone and bye bye. Okay.